Okay, what we have done till, last lecture, we were doing special theory of relativity, okay? We'll be starting now the gravity, okay? So first we will review the Newton's laws of gravitation, okay? Then we'll look at the equivalence principle, okay? What kind of ideas, okay, or what is the concept that led Einstein to formulate his principle, okay? So let's review Newton's laws. This is very important. Okay, so this is an action at a distance principle. What does that mean? So if you act to force on certain object, it will act instantaneously. Okay, with an infinite speed. The gravitational interaction between two bodies occurs at infinite speed, not at the finite speed. So that's why we call it as an action at a distance principle. So this is our force law. Okay, so it depends upon the distance of the separation. Let me write as r. So it's attractive nature. Let's consider some point mass m. Okay, so g is the Newton gravitational constant due to Newton. M is some point mass on which we are calculating. Which gives us actually the gravity. And let's take small m to be the test mass divided by r square. Okay, so you can think, let's say some body. Okay, so let me consider it this way. So you are having some mass here. We consider it as a point mass, and you take a test mass m here. So test mass we consider as a small object or infinitesimally small mass which does not create its own field. Clear? So which does not influence actually the field created by this very mass. Okay. So as in the electrostatics, what we know, in electrostatics, if you are having Q as a charge of a particle, you always write it in terms of this E, electric field, clear? In terms of the field. Okay, Q is the charge, and this is how you write the force. Okay, Q defines the test charge. In the same manner, we can redefine this force equation, okay, by defining some field due to gravity or the gravitational field, okay, which you call usually the acceleration due to gravity. Okay, so if I define the acceleration due to gravity, or I will not use it as acceleration due to gravity, I will simply use it as a gravitational field. Okay, so G of R, if I write it as like this thing, okay, then I can always define my force law like m g of r. Okay, clear? So this defines your gravitational field intensity, or simply the gravitational field at a point r. Okay, so now we can redefine it in terms of the flux. Okay, let's consider some space. Okay, let's consider certain volume enclosed by some surface S. Okay, and there is a mass distribution within this very surface. Let's say you are having some mass here, some mass here, some mass here, arbitrary distribution of the masses. Okay, you can rewrite this kind of law as like this thing: integration over the closed surface, this gravitational field ds. Okay, so that's simply equal to minus 4 pi g times m, and m is the total mass enclosed in this very volume, enclosed by this very surface. Okay, so it is same as the Gauss law. Okay, so this is just these things you have already done at your lower classes. I'm just repeating these things, okay, because they will be useful. Okay, so now if I write rho to be the mass density, okay, clear? So then I can write this total mass within the volume as d3r rho of r. Okay, so if I consider rho of r to be the mass density, okay, within this, let's say within this surface S or contained within the volume V, then I can write this total mass in terms of this. Okay, so you apply Gauss divergence law here. Okay, So now apply Gauss divergence law on the left hand side. What you will get? Are you getting my point? What I am doing? Huh? So apply divergence theorem on the left hand side. So it will be simply integration over volume V. Okay. Then divergence of this field G over volume V. So that's equal to minus 4 pi G integration M. You can write as integration over volume rho of R. Okay. So what it gives me? It simply gives me a differential form of the Newton's law. Okay, 4 pi G rho of R. Okay. So this is the differential equation. Okay, giving us the same what Newton's force law is giving us. Okay. Okay, or the Newton's law in the differential form. Okay, so now let me define the potential, the gravitational potential. The way we define as the electrostatic potential, I define the gravitational potential as this way, some phi. Okay, so we define such that the gravitational field will be calculated from this phi. Okay, clear? Got it? Okay, so now if I use this gravitational potential there, so what we will get? So from that very equation, you will get nebula square phi. So that's equal to 4 pi G rho of. So this is your Poisson equation for field phi. Okay, now we'll use phi as trajectory. Okay, so let's figure out the trajectory of the particle. What is the equation that governs the trajectory of the particle? Okay, so you simply have this force equation as force is equal to me. Clear? Got it? Or in other words, you also have this kind of equation, F is equal to mg. Okay, so you can, or in other words, you can write it as m d2r by dt2. So this is all the Newton's equation. So what it gives me? So this m cancels on this side. In a moment I will tell there is a conceptual point involving here. Now look here. Okay, so in a moment I will tell you. But let's cancel this m on both sides. What it gives me? So it gives me the trajectory of the particle in the gravitational field, and it's independent of the properties of the given object. Clear? So it is independent of the mass. Is it true? So does this, okay, so first tell me, does this give us the trajectory of the particle? Because this is the double derivative of r, you just integrate it over, and if you know what is the form of g, you will get actually r. Okay, so this equation defines what? Okay, so it gives us the concept that the trajectory of the particle only depends on the initial condition. It does not depend upon the properties of the particle. Like mass, it is independent of mass, it's independent of what? Charge, and it is independent of any intrinsic property of a given substance. Okay, so in other words, if you take two particles of whatsoever they have the mass, give them the same initial conditions, they will follow the same trajectory. Clear? Because it does not depend on any kind of mass. Okay, so you can rewrite this thing in terms of like d2r by, so this is important equation, g you have defined as gradient of phi in terms of the potential. Okay, so this is all about this Newton's law of gravitation. Now let's look at what are the problems with Newton's law of gravitation. First thing is, now if you look at this equation, last equation, it treats actually space and spatial and the temporal components differently, is it? You are having a double derivative on the left hand side and you are having a single derivative on the right hand side. Special theory of relativity says you treat both space and time on equal footing, and it's not true in that very equation. Clear? And now let's look at another example. Let's think of the planetary motion. Okay, so let's think you are having Earth here, and then you are having a sun here. Clear? Let's say a sun explodes. Okay, sun explodes completely. Clear? So what will happen? So the Newton's law of gravitation tells us instantaneously it will affect the Earth. Clear? So, but special theory of relativity says us what? what is special theory of relativity says? It will take at least 8 minutes because the interactions travel at the speed of light. Clear? So since the interactions travel at, there is a finite speed or the finite velocity at which the interactions travel, so it will be only in a finite interval of time this earth will receive the signal that sun has exploded. Is it clear? So that means our Newton's law are not compatible with special theory of relativity. Clear? Samushaman? And another point is that how this interaction is mediated between the two. Let's say, give us the concept of how this interaction is being mediated. Let's say if you are having two charges, think there is an actually analogy between electrostatics and the gravitation, the Newton's law of gravitation. Okay, so in the electrostatics, when you take two charges, okay, or in the electrodynamics, you take two charges that are interacting with each other, whether they repel or attract. Clear? So there is a certain kind, there is a mediation of that very force. Okay, by what we call the electromagnetic field. Okay, electromagnetic field mediates this kind of force. Okay, so what is the field that is actually mediating this very force? Samashivan? Or what? Because it is not electromagnetic in nature, it's a different kind of force. Okay, Newton's law does not give us any kind of idea how this force is being mediated between these particles. Okay, and actually it is the Einstein's theory that says it is the geometry of around or the space-time around a given massive object that helps us to mediate through gravitational interaction. Okay, got it? Samajh? So what are the problems with the Newton's law of gravitation? Clear? Any question? Okay. So now let's move to okay, so let's take a mass m, some kind of mass m. Okay, active force on it. You apply force on it. Okay. What will happen? So Newton's law says, Newton's second law says F is simply equal to what? M times A. So this M arises here in this Newton's law, arises as a reaction to this very force. Clear? Or you can think this M as a mass, as a response to the force acting on a given body. Okay? Clear? Samashima? We call this mass as the inertial mass. So any kind of force, okay? So this is the idea. This was, before Newton, people know it, okay? Okay, or at least you can say Newton identified. You can be having these kinds of things. You can be having an inertial mass that reacts to any kind of force. You apply a force on a given body as a response, okay? So you get actually the mass. Okay, think of you are having an inductor, is it? You apply actually current or the voltage through the inductor. What it gives us? It gives us actually the inertia in that very system, electromagnetic system. Clear? So that inertia, okay. So here you can think that inertia as the response to the external voltage through the inductor. Clear? So similarly, you can think this M. That's why we call it as an inertial mass. Okay. This is an inertia that a body gets when you apply a force on it. Okay, clear? Now another thing is, if you have this very equation, F is equal to M. Suppose let's take M to be the test mass, okay, and put it in the gravitational field. It will behave like this thing. Clear? So what this M will give me? This kind of M. This M will give me what? As a response to a particular force, that is gravitation here, the gravitational force. So that Mi, that is a response to any force, whatsoever force you are having, okay? Because force gives you actually the inertial properties, is it? Any arbitrary kind of force you are having there, that Mi will arise, clear? But if you are having a particular force, let's say in the gravitation, this M will behave like this thing, clear? A given object will behave in the gravitational field from the Newtonian perspective like this thing, clear? Samashima, then we can interpret this M to be the response to the gravitational field. We call this mass to be, let's call this as mg, gravitational mass. Okay? So we have identified two types of masses. Let's say an object, okay, you can think this mg as a gravitational charge. Think in terms of the electrostatics. F is equal to Q times E, clear? So what this is there a, analogy? So G is the field, E is the field, F is the force, F is the force. Then you can analogously say this mg is actually a gravitational charge. Because when a given object interacts with the gravity, it will interact through certain kind of property. Let's call that property as the gravitational mass. Clear? Got it? So we have identified two types of masses for a given object. Okay? Now let's work out, let's equate them. Okay, so then I can write this MIA is equal to mg. Clear? Or in other words, the acceleration, okay, a body gets, so it's something proportional to, or it is equal to mg by mi times. Clear? Got it? Okay, so now let's take two objects of, two different objects. Let's say one object is copper, one object is iron, and another object is feather. Okay, so that means completely of different composition. Think of two bodies, A and B, of different composition, of different nature. That means composition. Clear? So what does that mean from this very relation? It means A for object A, that's equal to this ratio mg/mi. For object A, G is same, because you are where? You are putting both the objects in the gravity. Clear? So you take two objects. Let's say I am taking this cap, okay, this pen and this brush. Clear? So both are having the different composition of different in nature. Clear? And you are putting them in the gravity. And this G will be same for both the objects. Clear? Okay, only this ratio will be, okay, so for the timing we'll take this ratio different for the both objects. Clear? So I will have this, because they will be having, they will accelerate differently. Clear? Okay. This is very important point to understand. Okay, so I will be having like this. So what does it mean? Okay. Okay. So we are having, that means if this ratio is not equal to 1, let's say for the time being, that means both the objects will accelerate differently. Okay, but we have just seen, okay, it's actually the idea of the Galileo. Okay, so we have just seen d2r by dt2, so that's equal to what? Okay, so that's equal to g. Clear? So it means if you are having two objects, they will trace out the same what? Trajectory. Clear? So, but it is not clear from this very equation. Why? Because we have already equated, you had actually m on this side, m on this side. You are having this mg and what? Mi. Clear? So you have actually compared these two equations, the inertial part and the gravitational part, is it? And you have actually cancelled them. In that sense, you said they will only depend upon the initial condition, not on the properties of the objects. Okay, now what to do? It was actually Galileo. It is actually an empirical result. It does not have, proof, but it has an experimental proof. You can verify it experimentally. What Galileo did? So it is before the Newton. Okay, so this empirical result. What he did? Okay, usually we say you drop two objects in the vacuum, they will fall with what? The same acceleration. Clear? So whether you are having a heavier object and a lighter object, they will fall what? In the same way. So that means in a gravitational field, okay, so both objects will undergo the they will undergo under the same acceleration. Okay, so in other words, this AA and this AB should be what? It should be same by Galileo. Okay, if you drop two objects, they will fall with the same acceleration. Clear? Got it? So this is a famous Galileo's experiment. So what it gives me? Okay, now tell me. So it gives me this mg by mi for an object A. This ratio is same for the object what? B. Clear? So in other words, if you are having a ratio for one object, same as ratio for the another object, in other words, this ratio should be constant. Clear? Look here, you are having mg mi for an object A, it is same as what? For the other object. So it means this ratio must be what? A constant. It is only then possible it should be same for what? Both the objects. Clear? So it gives me what? This mg by mi is equal to constant. Okay, and it has been found, okay, that this constant is approximately equal to 1. Okay, so initially it was found, okay, what Galileo did, okay, so Galileo found it to be up to the order of deviation up to the order of 10 raised to power minus 3. Okay, but today we know it's up to the order of probably 10 raised to power minus 17. I don't remember exactly the figure, whether it is 10 raised to power minus 17 or 13. Okay, got it? The deviation from a given mass from the another, I mean this very object. So let me write that very quantity. So you don't need to derive it. You just need, because this will form our basis. So you are having, let's say this delta, it's something mg by mi for an object A minus mg by mi for an object B divided by mg by mi for an object A plus mg by mi. This is very trivial. Okay, it's magnitude. So it's of the order of, let's say, 10 raised to power minus 7. This constant. Okay, so that means for all practical purpose, this mg is same as what? So we are having the first point here, the inertial mass is same as what? Gravitational mass. Clear? So that we are having only one kind of mass. So this is the empirical result forms actually the foundation of the geometrical picture of the gravitation. Okay, how? Okay, so it is actually this kind of idea, this Galileo's result. This influenced Einstein. Okay, you are having two objects of different kind, they fall in the same way under gravitation. Clear? So this he called as the happiest, ideas of his life. Yes? Huh? So let's go to this very principle. Okay? So we have the first result at hand. This inertial mass is same as what? Gravitational mass. That means all the objects fall in the same way under uniform gravitation. Clear? So these experiments, to show this as equal to, it was actually at Wash. So you should know. So at Wash was actually the person who performed series of experiments to prove this is same. In the modern times. Clear? So this inertial mass is equal to gravitational mass was first proved by Galileo. He made some kind of calculation. It was not actually. Usually historians says he dropped it from the Leaning Tower of Pisa, but it's not like that. So he was actually studying the rolling bodies on an inclined surface. In that very way, he arrived at this conclusion. Okay, so his order of magnitude was actually 10 raised to power minus 3. Clear? It was later on defined by this at Wash. Okay, and recently people did it from actually different methods. Okay, 1977 around. Okay, so they figured out it actually 10 raised to power minus 17 or I'm not correct. You should look at it. It's beyond actually 10 raised to power minus 12. Okay. Okay. So let's go to what we call the equivalence principle. Okay. So equivalence principle, the first part, it has several parts. Okay. So what we call actually the weak equivalence principle. So let me write. The first part is something what we call what? weak equivalence principle. So it is this restatement of this thing. Mi is equal to mg. Inertial mass is same as what? V. Let's think of an elevator. Okay? You think of an elevator. Okay? So there is an observer inside the elevator. In this very elevator. Clear? So let's put it in the uniform gravitational field. Let's think on the surface of the earth. Oh, okay? So there are no engines at all which is driving this elevator. It is under the free fall. So what? Let's say he is dropping an object there. Okay? Or he has some object with it. So what he will observe? Because there is no gravitational pull, it is under the free fall. Both the bodies will fall in the same way. Clear? So with respect to this very observer, this object will be always stationary. It will be always there because it does not experience any kind of force. Clear? Under free fall, they will be the same way. Samajh? So what it means? Okay, let's put it this way. Let me put another way. If you are not able to understand, think of an elevator. Okay, you accelerate. Okay, so in the free fall, you are actually cancelling the gravity. Clear? But you want to create the gravity. What you do? You simply accelerate an object. Clear? So let's say if I have to figure out how much gravity is on the earth, it is 9.8 meter per square second. Clear? And I am accelerating my elevator at the same rate. Clear? So, and in that very elevator, there is an observer, and he drops a pebble in that very elevator. What will happen to the pebble? So that will hit the bottom of the elevator. Clear? And this observer will never be able to identify whether the elevator is actually in the uniform gravitational field or it's accelerating. This is the crux of equivalence principle. Equivalence principle means acceleration is same as gravitation, uniform gravitation. Clear? So if you are having an accelerating effect, it is same thing what? As a gravitational effect. Huh? Are you getting this point or not? Huh? So in free fall, what you are actually in free fall, what you are actually doing? Okay, so let's say some objects under free fall. Okay, so anybody is having a bottle, plastic bottle. Hum bottle, sir? Yes, give it to me. Isha dukaan par invest kin ho? Huh? Okay, good. So I will provide you another bottle. Huh? So this is it, sir. So while we can taste it. Huh? Yes, great. Okay, so how it falls, this very water? It's because of the gravitation, is it? So gravitation pulls it, falls down. Now if you throw it on the ground, so let's put it in, it is now under free fall. What will happen? So has water come out? Huh? So that means it has not felt any gravitation. So just wait it. So I think we should drop it from the higher place, huh? So that you will see. Okay, just come here. So this is the simplest of the So drop it from a good height. No, yoga. So okay. So now drop it. So have you seen? Huh? So what is not coming out? Why? Because in free fall, it's not feeling any kind of gravitation. Okay? Clear? So that means an observer in a free fall will not observe any kind of gravity. He will always feel weightlessness. How it is possible? So look at, since the equivalence principle, okay. So how is that possible? So if you are feeling weightlessness, how it's possible? No, how it's possible? So that means the acceleration is cancelling the gravitational effect. Okay. So when the acceleration, so okay, so what is the direction of the gravitational field on the Earth? It's opposite. So when you put a body like this thing, so acceleration is opposite to that Earth. So that means in the free fall, the amount of the acceleration is exactly same as the amount of the gravitational field. Okay? So much it cancels. So that's why you are not observing any gravitational effect. So in other words, if let's say if you are having some elevator or some observatory, you are moving it with the acceleration. Okay? With some constant acceleration. That means you will feel some gravitational effect within that observatory. Samajh? Clear? Equivalence principle simply says the acceleration is same as what? The gravitation. Here in the free fall, the gravity is opposite to that of the acceleration. That's why they cancel out. Okay? So this is the crux of the equivalence principle. Okay. So let me write the statement. So it gives me this thing. Physics in a frame freely falling in a gravitational field is equivalent to physics in an inertial frame of Earth. So this is very important. Okay? Got it? Because in the freely falling observer, you don't have the gravity. You don't. Okay, gravity and the acceleration are cancelled. You can think that free fall as the inertial observer without gravity. Clear? Got it? So it is known as the weak equivalence principle. Or in other words, now if you have to create the gravity, what you have to do? Let's say if here we have cancelled the gravity, is it? If you have to create the gravity, what you have to do? You accelerate a given object. Okay? And let's say if you have to create the gravity like the Earth, what we were having on the Earth, that means you accelerate that very object with the acceleration of 9.8. Okay? Then in that very object, in that, let's say you are accelerating an elevator with acceleration of 9.8 meter per second square. Okay? The observer within that elevator will not be able to identify whether he is in the gravitational field or he is in accelerating. Clear? So he cannot distinguish between the two. Clear? Samajh? So let's write it the other way around now. So we can have another statement. So the another way is like this thing. Physics in a non-accelerating frame with gravity. Okay, let's say G is equivalent to physics in a frame without gravity. Without gravity but accelerating at E. That means opposite to that of gravity. Clear? Clear? Any question? Okay, so now we have actually the definition of the inertial observer, who we call the inertial observer. Till now we have defined the inertial frame of reference with respect to what? With respect to a fixed star. Clear? So we said it is in the uniform motion. Clear? So it is in the uniform velocity where Newton's laws hold. Clear? Or Newton's inertial law hold. And we define, if we have to figure out an experimental way, what is an inertial observer? You say some fixed star is there which does not change. Okay? You call an inertial observer with respect to that kind of star. Okay? So a certain kind of objects. Now here, what an inertial observer means. Equivalence principle gives us actually the physical way to understand the inertial observer. An inertial observer is simply a frame having no gravity. If you are having a frame of reference without gravity, so that's our inertial frame of reference. Okay, if you are having now the frame which is having the gravity, that is a non-inertial frame. Clear? So now if you look at the Taylor paradox, what we did earlier, so there I have not mentioned any equivalence principle. Clear? So you are having an accelerating object and a non-accelerating object. Non-accelerating object is an inertial frame without gravity. Clear? And the accelerating object is what? It's actually the gravitating object. Clear? So there is a gravitation involved in that. Okay? So in other words, the dilation, these time dilation effects are due to what? The gravity. It is the gravity which is influencing the object. Clear? समझ आओ from the equivalence principle. Okay? Any question? So let's look at the implications of this very principle. Okay, so there is another second way. Okay, what we call a strong equivalence principle is that all laws of physics should be the physical phenomena in one frame of reference should be same as in the another frame of reference. That means physical phenomena should not be dependent on the coordinates. It should be coordinate independent. Clear? Got it? So if you move from one coordinate system to the another coordinate system, okay, so you can say the physical phenomena remains same. Okay, so let me put it this way. So think of the free fall again. So you are having an elevator, okay, which is under free fall. An observer is there. Okay, I have nothing to do. Now we know there is no gravity at all, because gravitation is cancelled by what? Acceleration. Okay, under the free fall. Okay. So now an observer who is sitting outside, what he is watching? If you are having an observer outside the elevator, let's say I am here and there is an elevator going under free fall. What I am seeing? I am seeing actually an accelerating object. Clear? Because a body which falls under free fall, let's say this goes under free fall, it's actually an accelerating object for me. Clear? But there is one more force. For me, there is actually the Newton's law of gravitation. Let's say F is equal to mg. So that's also there. Clear? So if I am saying the physical phenomena should be independent of the coordinates, that means whatever the phenomena is being observed by the observer within the elevator, it should be same for me. Clear? So that means for me, I have to calculate both effects. What is the effect of the acceleration and what is the effect of the gravitation? Okay? So both effects should, okay, give me the same result whatsoever is the result inside the elevator. Clear? समझ आओ? Got it? So that we call as, although it's also the restatement of this equivalence principle, we call it as a, for the time being, we will call it as a strong equivalence principle. Clear? So समझ आओ? Okay. So physics should be independent of the coordinate choices. So strong equivalence principle. This is very important. Physics should be independent. Physics of a given phenomenon. Okay, of a given phenomenon. You should not say physics book independent of coordinate choices. So once these principles are clear to you, you will be able to do many things. Clear? Okay. So now let's figure out what are the implications of this very principle. Okay. Let's look at the implication and how to go. Okay. So let's try to figure out what are the implications. And there is a methodology to obtain these implications. Okay. So we will take this elevator. Think whenever we discuss an observer, he is in the elevator. Clear? So we will be using this kind of procedure. Okay, so let me write this procedure so that you will understand it. Okay, so the first, okay, so this is the general procedure I will be following. Okay, because equivalence principle is it's an you can think it is an argument. When you are having an argument, based on that kind of argument, you prove certain things. Okay, then you have to go in a logical way. Okay, reasoning what is happening with that kind of argument. Clear? For the time being, it is some hypothesis for us, and we are checking the application of this hypothesis whether we get the true results or the null results. Clear? So that's why we need a given procedure. Okay? Okay, so let's take the first thing. So we will consider an observer. Okay? So one first considers the description, okay, by an observer inside an elevator. Okay, in free fall. What is the equivalence principle saying in the free fall? Huh? According to the equivalence principle, there is no gravitational effect. Okay, so when there is no gravitational effect on the free fall, so that means I can apply the results of the special theory of relativity. Clear? So special theory of relativity is something which is, where you don't incorporate any kind of gravity. Clear? So okay. So according to so there is no gravitational effect. So since there is no gravitational effect under the free fall, we call it as an inertial frame. No? In this inertial frame, so and special theory applies. Okay, so this is our first, step to proceed to figure out what are the implications of this equivalence principle on a given physical phenomenon. Okay, we'll be taking an example. Let's say the time shown, proper time shown by the clocks, or we'll be taking actually the example of the the bending of light by the gravitational field in a moment. Okay, clear? So now let's take the second thing. What we will do now? So I am having in the first case only the observer in the free fall. Clear? So now let's consider another case where we are having two observers. One observer is under free fall, another observer is watching this free fall. Clear? Got it? Okay. So next step, one then considers the same situation from an outside observer. Okay? From the point of view of an outside observer. Let's call that observer as observer B. Clear? So we'll call this observer as observer B. Okay? Yes? Any question? So for this observer, what we are having? So if I am observing from outside this free fall, what I am having? I am having now two types of things. One is the acceleration for free fall, another is the acceleration due to gravity, or there is a gravitational field. Clear? So this observer, so we need to consider two things. One is acceleration, another the gravitation. It is which observer? Who is sitting outside. Okay? So he is looking at these two things. Okay, so the observer who is sitting outside, what kind of observer is that? He is an inertial observer. Clear? Because he watches the accelerating object, or he watches an object falling under the gravitation. Clear? So himself, this observer B is actually an inertial observer. And when he calculates what is the force of gravity on that observer who is under free fall, he will use the Newton's equation. Clear? We are using only non-relativistic phenomena for the time. So he will be using this F is equal to mg. Okay? Here. Okay, so now, so these are the two viewpoints, and there should be now third viewpoint, because I have to obtain what is the result inside the first elevator, inside the first case. Okay, inside the elevator. This will not give me the result inside the elevator. Clear? Got it? It will simply give me the results as observed by me of that kind of free fall. Okay, and I have to match these results. What are the results I have obtained in the case 1? Clear? समझ आओ? Okay. So the third point is, so I will, if you are not able to grasp it quickly, so let me go slowly. So the combined effects of this acceleration So acceleration is where? In the second point, and the gravitation is also there. And the gravity as seen by observer B, that means outside observer B must reproduce what? SR results. Why? Why are the SR results in the case 1? Clear? So when they reproduce the SR results, then I can say my equivalence principle is valid. Why? Sorry, that means I have actually employed the equivalence principle, because in the equivalence principle, the strong one, we have what? The physics is independent of the coordinate choices. Clear? So your hand coordinate system 1 there, coordinate system another there, both should give you the same physics results. Clear? Okay, so let's start with an example. Let's take first example. So if you have any question, just tell me. Okay, so let's take example 1. So we'll take a qualitative idea of bending of the light. Okay, so let me put a qualitative idea. So quantitatively we will do it later on. Okay, first I will give a qualitative idea. So okay, before doing this bending of light, okay, so let's say you are having an elevator, correct? So let's take this kind of elevator. Okay, so it's static, it's at rest in the gravitational field. Okay, so you are having an observer here, and he throws a ball. Let's say, so this observer throws this kind of ball in this gravitation. Suppose I am here. Let's say elevator is fixed with me. I am throwing some ball. What is the trajectory of that very ball? In the gravitational field, it's parabolic. Clear? So it will go like this thing. Again. So let's say I have to figure out the y coordinate. Let's say, so this is a straight line. So y is equal to half of gt square. Clear? Over a time period. Is this the case? If I throw a certain object, what it will do? So the height through which it falls is given by what? Y is equal to half. Let's say x is equal to half of gt square if you take x as the coordinate. Clear? Okay. So now, so this is one of the viewpoints. Now let's say if this elevator is under free fall. First let's take now this elevator under free fall. What will happen to the ball? So if I release, let's say I am under free fall. So I will release the ball. What will happen to the ball? It will be stationary with respect to me. It will not move. Okay? So that means both me as well as the ball will undergo free fall, will observe no gravitation. Clear? Okay. So now if I do another way, so I accelerate this elevator. Okay. So let's accelerate this very elevator. Okay, instead of rest, let's say accelerate it with the rate g. Okay, g is the value of the gravitational field. What will happen to the ball now again? So because of the equivalence principle, this observer will not able to distinguish whether he is in the gravitational field or accelerating. So that means by equivalence principle, since I have accelerated it with the acceleration of g, so by equivalence principle, acceleration is same as what? Gravitation. So that means when he throws a ball, what will happen to the ball? It will follow a parabolic trajectory. Clear? So that means we have got the same results. I mean, you are having an elevator at rest or elevator accelerating at g. Clear? Now let's drop. Okay, so if I look at this elevator from the outside now, let's say you are having elevator undergoing a free fall. Clear? For an observer within that, what he will observe? So he will not observe, it will be stationary with respect to the observer there. But an observer who is sitting outside, what he will see? it will appear to move in a parabolic trajectory, because let's say at time t equal to 0, this person throws a ball, clear? But it will remain stationary with respect to him. But an observer who is looking at it after a time t, this point has moved, clear? This point has moved to the another point. It will appear as what? A parabolic trajectory, clear? Within that, it is what? Stationary. Got it? So, now let's think of the light. Okay, let's think of the light. So, you got it? Okay, think of the light now. Okay. So, let's say you are having this kind of elevator again. Okay, it's under free fall. Okay, let's look within this very kind. Okay, I have not said, I have said it appears to move along a. So, remember the word appear. Clear? So, it is the same thing when you drop, let's say, in the water, some stick, what happens? The stick bend. So, what happens? It appears to bend. Clear? So, that means there is some electromagnetic interaction which makes it to appear bend. Clear? So, you know the properties of the waves and so on. It goes like that way. Now, let's think you are having the point E, some emitter, and let's say you are having a receiver R here. An observer throws, let's say, a light beam, a photon, clear? Or a light signal, he sends it to the receiver. Within the elevator, if the elevator is under free fall, let's say this elevator A is under free fall, but an observer who is sitting inside, what will happen to this light, to him? Because it is under free fall, so the height at which it is emitted, it will be received at the same height, clear? So that means this will appear stationary with respect to the observer A, who is under free fall, clear? Now let's say if you are having an observer who is sitting outside, you apply the same analogy. This is actually very important point, although it was very simple to see, but people earlier to Einstein, they knew light traveled in the straight path, clear? So it does not bend at all. So that's why they have not paid any kind of attention to this kind of result. It is so simple, but it's very profound. Okay? So now let's say if you are having now this observer watching, what will happen? So let's say this elevator is under, okay, so this is under free fall. To this very observer who is sitting here, so this light will appear to bend. Clear? So because he is looking at the accelerating effect here. So this is under acceleration. So he is observing this light to bend under this kind of acceleration. But equivalence principle says acceleration is same as what? Gravitation. Clear? So that means light bends in what? Gravity. So in other words, the photon is gravitating itself. So this kind of the proof to this very result came. Okay, so the bending of this light came just after the discovery of this concept. Okay, in 1922, there was a solar eclipse. People took the photographs and analyzed it. They analyze during once they developed those screens, they figured out the background stars to the sun. Okay, so how it is possible? So how it's possible? If you have actually the bending of light along what? The massive object. So let's say if you are having some object, you are having a massive object. By this very argument, so the light is bent. Clear? Let's say you are having the observer sits here. Okay, so let's say an observer sits here. So clear? He observes a star here. So why it will appear? So let's say if you are having a star here and you want to observe it in this very direction, why it will appear? Because the light bends, it will come, you'll figure it out like this. Clear? It's something actually, in reality it's like this. The way if you are throwing a stick inside what is happening. So you can figure out how much it has bent. Clear now? Huh? So where that stick appears? Let's say if you throw it like this, the stick appears near to you. Clear? So that is bending happens, but actually it's not there. it's at some other place. There is an apparent position. So this is actually the real position. Once you try to detect it, where it happens to be? Here. So you need to figure out, okay, so we'll get actually the calculation of this very angle. Okay, so in the next lecture we'll try to figure out how much this angle is. Okay, so experimentally I should figure out this kind of bending of this light. If this matches with the experimental data, that means light is truly bending near the massive objects, or the gravity bends the light. This is a very important, conceptual thing. You should, if you have any question here, just tell me. If you have any question, just tell me. Everybody has got this argument? So this is a very difficult argument. This is very difficult to understand. So why people have not realized it earlier? It is because of the equivalence principle. Because equivalence principle says acceleration is same as what? Gravitation. That's why gravitation causes bending of the light. Okay, you can apply this kind of argument. Okay, suppose if you are having, since you are in the uniform acceleration here, clear? So value of gravitation is 9.8, but it's due to Earth, clear? And Earth is a small, very small object. But if you are, so that means this light is bent because of this gravitational field of the Earth. Okay, so let's get a simple calculation. Okay, before that, if you are having now the massive object, that means the gravity is huge, value of G is very huge, clear? So that means the bending of light will be appreciable. So now let's take your hand 30-meter laboratory. Let's assume you are having an elevator of width how much? 30 meters. Clear? So how much time it will be? It will take light signal to cross from E to R. So it is a finite time. Clear? So it's approximately equal to, so time taken from E to R is approximately actually 1 microsecond, or microsecond, 10 raised to minus 6 seconds. If I am having 30 meter this thing. Clear? So you can calculate it, right? So T is equal to, so ER length divided by C. So what is that? 30 divided by 3 into 10 raised to 8. Clear? So how much is that? 10 into 10 raised to, what is it? Minus 8. So that's approximate. So that's actually equal to 10 raised to minus 7. So that means 10. So this much of time it will take. Now let's calculate how much through how much height it falls. So y is equal to half of gt square. So how much is that? Half of, what is g? Let's call it as 10. What's t square? So it is 10 raised to minus 7. So that is 10 raised to minus 14. How much is that? Half of 10 raised to minus 30. Clear? So meter. Sorry, yes, half of this thing. So that's equal to 0.5 into, okay, so let me divide it by 10 raised to minus 12. Clear? So meter. So how much is that? 0.05 what is 10 raised to minus 12? Is it picometer? Eh? Yes. Picometer. So how small it is? Eh? Even though your lab is how much large? So now if you use the G very large, okay? So if G is very large, then you can lower down, let's say, the powers of this thing. Even you are having large G, still you will not be, let's say if G is 100, for example. Let's say G is 100. So what will be having? It will be simply 10 raised to minus 12. So that's approximately equal to 5 angstrom. So that's very small length through which it bends. So that's why essentially geometrical optics says light travels in the straight line. Okay, always. So clear? Any question? So we'll go beyond this. So this is the horizontal picture. We'll look at the vertical picture. If you are throwing a signal from, let's say, bottom to top or from top to bottom. Clear? So we'll figure out what is happening. Okay, any question?